Hello everyone, this is Anil and you are watching the YouTube channel Anil Kumar Classes. So I welcome you all in my YouTube channel, and if you are new on this channel, then I request you to subscribe the channel, like the video, give your comment, and if possible then share this video with your friends. So now we are studying Lagrangian Dynamics. In Lagrangian Dynamics we have studied constraints, and in last video we have seen the types of constraints or classification of constraints. So today we will continue from that. So in introduction video only, I have told that Lagrangian dynamics is nothing. This is mathematical. It won't give any new concept, but it will work. It will make our work easy. So it will help us to solve the problem by easy way. So let me take. I will take one formula. I will take from what classical mechanics, or I want to say Newtonian mechanics, and we will continue from there. So in Newtonian mechanics, I think you know that one formula. What is that? We can write F is equal to P dot vector. If you don't know, then it is nothing. It is easy. You know that second law of motion. Second law of motion. What say F is equal to ma. And if I want to write it another way, I can write F is equal to dP by dt vector. I can write, and if I want to and if I, what can I do? If I d by dt, if I replace with a dot, so I can write it like this: dp dot. This dot will say as d by dt. That's it. But here be careful what that means. Dot means it down. We can't write d by dx. D by dy. For time, respect of time only, we will use that dot. So here we are using. So this formula is the same. So let us understand what is that formula, and then after that we will move. So in this formula, F is total force. So F is total force, and P dot is nothing but change in momentum with respect to force. Means that however that force will be applied according to that momentum of a system or particle will be changing. That both are equal. So if we see total force, then total force is nothing but F is external plus F internal. And F is external. What is F is external? Is F applied force. F applied, I can write like. And internal force, there are two types of internal force. If we see it, one is that let me see it right here. Internal force. Internal force, one is dissipative force, internal force. What is that? This is nothing but it will oppose the motion of particle, or it will be working the anti-direction of a motion of a particle. So it will be work to decrease that total energy of particle. So this one is, and for example, if you have example, then that frictional force. Viscous force. So these are the example of a internal means dissipative force. Second is internal force is which act as internal force, which is that force of a constraint. Force of constraint. So the constraints, because of constraints, we have to consider it an internal force. So what is that? First we will understand what is constraint. So the force because of happening because of that constraint is called force of constraint. Like for example, if I see here this box I am taking m mass. So here what is that box? So what is the constraint of this? Because the constraint is this mass is m is movable in AB plane only. It can't go down. It cannot go down completely. So how it is moving? It can move this one. So it is free to move this direction. But it can't come out downside. So for that one, AB, if we see AB plane, it is forcing this m mass to this one. This F is applying. So that force which is applying force, and that which is restricting to come that inside or come in this side, that mass, that is called force constraint. Similarly, if we take that pendulum, this is my pendulum, and I take 80 time here. Then here also that pendulum is restricted to move in this path. So for this, if I see here, then force of constraint will be here. If I take this position, then it will be this side, this side, this side. These are the force of constraint. So you can take or consider all the force of constraint. So these are the two forces. Here for this formula, we will consider that dissipative force is 0. So now if we move further, because using this, so I have total I can write. For external force, which I can write the applied force, and internal force. There are two types of. One I get 0. So second is force of constraint. So I can write this is. So if I replace it with this, then we can write this one to this. So it will be applied plus force of constraint is equal to P dot. And P dot I can write like d by dt P vector, and I want to again write, then I can write it d by dt and v. M is constant, so M is log, and d by dt v vector. And if you know, then v to v we can write dx by dt. X is a xi some particle. So if I want to replace, then we can write it like this: d by dt square, or d square by dt square xi. So this will be force of applied plus force of constraint. We can write dt square. So these things are very basic things you already know. So now we will try to understand this formula. So this is force applied force we know. This is force of constraint, and because of that means we can define this one. So for this one we should know applied force of constraint. So now we will understand force of constraint, how it is and what is that. So again we will move that for both example which I have taken. This is an example one. First I take the and second I taken. And if you take any another example, but it should be holonomic. Now we are discussing all these things with holonomic. We did not take that non-holonomic. So holonomic and plus Scleronomic for this one. Rheonomic we did not take here. Rheonomic will be that the equation will be time dependent. So we will see the next time. So here force of constraint. Here if I see that force of constraint is this side, and in this one if I say position and position, this is force of constraint. This is force of constraint. But that system of particle is moving this direction, right? If I see, then this is also moving this direction. What I mean, the angle between the both displacement, if I take dr, here also if I take dr, displacement, and both are perpendicular. So here to define, I can do one thing. If I take that dot product of dr, I take for work done integral we know f dot dr. If I take, then angle between is 90 degrees, so I can do like this. For force of constraint, I can write dr cos 90 degree, and cos 90 degree we know 0, so it will become 0. So this problem will get solved. So if I do like that, then our formula is like plus force of constraint equal to, let me write again, it is equal to p dot vector. So this is p dot vector, and if I take in this side, then I can write like this minus p dot vector, and it will be equal to 0. If I multiply both the side with dr, then I can multiply. So it will be, and I will take it, and force of constraint I will take outside. So it dr plus force of constraint dot dr is equal to 0. Because if I am multiplying anything with 0, it will give 0. So equal to 0. And this one I have shown you, it will be 0 because that force of constraint will be always perpendicular to the that motion of a particle. For holonomic and scleronomic, don't take for that rheonomic. Rheonomic it won't be perpendicular. So if I take dr here, it will be perpendicular. Perpendicular means that angle between dr will be 90 degree and cos 90 degree we know 0. So it will be 0. So our problem will become easy, and this time will go 0. So it will be dr is equal to 0. This is for one particle. If we see then another a system of particles, then we can write like this. So integral for all particles we take, then it will be valid for all. Now these examples I have taken, but there are some examples means things we there for force each of constant force means here that force of constant we know that is perpendicular, and we can calculate if we want. We can calculate and we can make it 0. But if we take let's take example of a rigid body. Rigid body, then let me take a particle, and if I want to show the position of that, then this is x-axis, y-axis, and I have some particle inside that. So I want to show position of that particle, then I can write this is Ri, and this is Rj vector. So if you know the property of a rigid body, what do you know? We know that it means distance between every particle in rigid body will be constant, it won't change. So I can write like this. Ri minus Rj, it will be constant, and Ri minus Ij I can write Ij. So Rij is equal to constant. So here what I mean, here we don't know what is the force between two particles. Here if I take this particle and this particle, I don't know what is that force, but I know that effect because that means distance between the both of particle or any particle random if you choose. The distance between two particles it will be 0. So for using that, I can do, what can I do? I can make that force because of that constant. If I take any random particle, work done because of that it will be 0. How? Let us see. So if I make it square, then I can write R square Ij is equal to C square, and if I differentiate with respect to dt or n, so it will be, so I can write like this. It will be 2Rij vector and drij will equal to, if I take this one it will be 0. So if you consider this one, then Rij, and if I multiply both the side with force, or not need to multiply with force, if we see here then Rij if we see that for more displacement, force will be acting that direction only. If I take, so it will be means force into drij, it will be means what will give work done. So here work done is equal to 0, and if you did not understand, then I can write like this. If I multiply here force 2Rij and force drij is equal to 0, and if I multiply the right side also, then 0 f into 0 is equal to 0 only. So what I mean that total force, this is some positive means this is Rij is some position, it is one, so it's not be 0. So possibility is that this will be 0. So I can write like this, drij is equal to 0, yani work done is 0. So using this one we can remove directly that if I take dr in dot product of dr here, so we can remove that term force of constant. So it will be easy for us to solve that equation. So these are, now this equation we got from holonomic and scleronomic. But what if I take rheonomic here? Then we'll see. That thing we will understand using example. So let me take an example. This equation I got from this. Let me write it here. I take applied and minus p dot and you see that rigid body. I have taken one example only. If you take any example, it will be zero. That work done will be zero. So you can use that integral multiplication. You can keep this again like I don't r I j d r I j is equal to 0. So for this one you can use like this. So for all particle, if you any particle randomly you can suitably follow. So you can write. Now let me take example. Same example I will take. This is my pulley and this here. So and this L length can be changed according to the time using this one. If I give that some rope here, it will go down, and if I take that, it can be made shorter. So let me consider it is means according to time that length is getting short. So if I take this example, this is our Scleronomic. So if we consider same formula here, F is equal to P dot I, and it will be F is equal to applied force plus force of constraint will be P dot equal to, and we can write like this, equal to 0. So now we will see. So in last for Scleronomic and holonomic, I what did I do? I took dr position here, and that angle between both that force of constraint and for displacement it was 90 degrees. So it got means if I do that work and then it got 0. Then let us see if this thing happen in this one also. So for here, if it is going to shorten according to the time. So if I am taking here, so it was here. So if it is moving in this direction particle, so if it length could be was constant, then it could like this, and it could come here. But I told that this length is decreasing, so it will won't come this side. If it come this side, then that angle between force of constraint, this is the force of constraint, and this is the displacement. Then that angle between them could be 90 degree. But this is the length is going to shorten, so according time. So it will be, or it won't come here, it will be like this. Let me take here. So if you take this one, this is displacement and this is force of constraint. So if you notice, then that angle between displacement and force of constraint is not equal to 90 degree. So if it is not equal to 90 degree, then it is difficult to remove this term from here. So what can we do? Here 90, if it could be 90 degree like this. If I take dot product here, and similar case which I have done in last time. So if I do dr method equal 0, so if I take here like plus minus p dot, and I'll take it outside. So dot dr plus constant dr. So if I see this one, this angle is not 90 degree. dr cos theta. So this angle theta which I take, this is not 90 degree. So if this is not 90 degree, we cannot make it 0. So for this one, what can we do? We how to solve this equation will be work easy. So here for this one, we will introduce a new term that thing we will see in next class, which is that virtual displacement and virtual means work. So according that we will means if we see this equation is x square plus y square is L square. And what is that? L is changing according to time. L is changing according to time. Then what I'll do, I can make some change, small change in this one. What can I do? If I make t is equal to 0, change in t is equal to 0, and I will make some smaller displacement delta r, which is very smaller displacement, then time is not changing. So if I see in this equation, so this equation is dependent on time, L is depending on time, means if I change the time, then it is length is going to shorten. But what can I do? If I make t is equal to 0, change in t time is equal to 0, so it will be constant. And if it will be constant, then it will be work like this, same which was in Scleronomic. So this angle between force of constraint and displacement will be 90 degree, and this term will be 0. This time if I got a 90 degree here, then your term will be 0, and it will be, we will make it like this. dr equal to 0 because it got 0. So for this one, next class we will see that what is virtual work, what is virtual displacement, all these things. So if you did not get yet, means here what we are doing, this equation is dependent on time. According to time, this equation is going to change. So what if I change that time, changing time back, if I make time, changing time 0, so this equation behave like similar, like this type of equation. That if I take, then simple pendular and I take 2, it will behave like this, because this length is not going to change, because the time, changing time is 0. So it is the same, then displacement angle between dr and force of constraint, it will be 90 degree. So if you take dot product, it will give 90 cos 90 degree, and cos 90 degree we know if this is 0. So it will be easy, then it will become easy again. We can apply that work done formula, and it will be get disappear, and we can solve that next. So today's class we will finish here, and we will see next class. So if you want to move in next video directly, sir, after getting video ready, I will provide that link of that video into description, so you can go directly. So see you next class. Bye bye.